This is Kyungjun Son from KAIST Teralab, Republic of Korea. My research title is Deep Reinforcement Learning Based Optimal Interconnection Design for 3D Cross-Point Array Structure Considering Signal Integrity. These are the contents. In introduction, I will talk about why the optimal interconnection design considering signal integrity is needed, and why we use reinforcement learning. Then, we will talk about the Markov Decision Process for interconnection design problem. Also, we used Proximal Policy Optimization, PPO, with clipped objective for deep reinforcement learning. And for the 3D cross-point array structure, we verified the proposed optimal interconnection design model and end with conclusion and further work. Introduction. With more fine technology node, SI issues at interconnection lines such as crosstalk and IR drop are important. There are trade-off relationship between crosstalk and IR drop, so the optimal interconnection design considering signal integrity is needed. It is hard to determine the optimal interconnection design considering SI issues without heuristic insights. Therefore, reinforcement learning can be the solution. Let me briefly introduce about Markov Decision Process. Markov Decision Process is defined by tuple SAPR, S is state, A is action, and P is policy, R is reward, and gamma is discount factor of reward. So as you can see, agent performs action AT at state SD. Then the environment returns the next state ST plus 1 and reward RT plus 1. So it is important to convert the interconnection optimization problem to proper MDP components. This is the overview of optimal interconnection design model using deep reinforcement learning. State, action, policy, reward of problem are defined for MDP. Also, policy is constructed to MLP, LSTM, and actor critic A to C model. And proximal policy optimization is used for updating policy. So, I will talk about the proposed model with more detail. So these are the MDP of our model. MDP of our problem. First, we define the state to current interconnection status. As you can see, the state is the vector with 0 and 1, which means the location of word lines and bin lines. And action is that add word line or bin line to previous state. So as you can see in the figure, add 1 in previous state vector. It means one line is added in 3D cross-point array structure. And this is detailed view of policy, also called agent. Policy decides next action from previous action and state. And multi-level perceptron MLP converts input state vector to high dimensional embedded vector. Also, long short-term memory, also known as LSTM, outputs the stochastic policy, and next action is sampled by that policy. For the reward function, the number of bits, crosstalk, and IR drop are considered. And discount factor controls the importance between instantaneous reward and potential reward. Therefore, the total reward equations are shown like that. And this is the proximal policy optimization with clipped objective for deep reinforcement learning. Proximal policy optimization updates the policy which decides the action considering reward proximally. So in the equation, at the first term, the PPO prevents excessively large policy updates and defines lower bound by clipping. And in the second term, the value function error term regularizes the actual critic, where prevent critics misestimation for future value using temper difference error. So with this model, we verified the model with scale variation like 16 by 16, 32 by 32, and 64 by 64. For the comparison, we normalized the reward as shown in the graph. In small scales, the model easily converged under 20,000 learning steps. However, in large scale with 64 by 64, the normalized reward graph is unstable, and it means that it is hard to find optimal solution and needs more time to learn. As you can see, in case of 64 by 64, the normalized reward of trained model is converged around 170. With the proposed model, the optimal interconnection is shown like that. We tested 10,000 samples with proposed reinforcement learning model. As you can see, the number of bits are satisfied, minimum requirements, and the interconnection lines are properly located considering trade-off relationship between crosstalk and IR drop. So, for the conclusion, we proposed reinforcement learning based optimal interconnection design model. Also, we defined reasonable Markov Decision Process tuples for interconnection design problem, and we verified that the reward of reinforcement learning based model is converged. For the further work, we can correlate to 3D EM simulation result of crosstalk and IR drop. Also, we can expand the environment for practical feasibility. Thanks for your listening, and feel free to ask questions or comments. Thank you.